This part should be 50 mm, but why is this one bigger if every filament shrinks? Hello, welcome to my tech farm, to another video which is not really created for the mass, but you who is watching this video are much more important for me. With my previous video, Laminar Flow, I lost 3 subscribers but I got 10 new, so the balance is still positive. And a friend of mine make a joke that, don't worry Igor, with this the average IQ of my subscribers is rising. Which is really good feeling for me, but not so good financially. Thanks to the Polymaker who is the channel sponsor, and thanks to my Patreon supporters, I don't really care about this part and I decided even to disable the ads during the video. Now let's talk about dimensional accuracy. Maybe you are familiar that every filament shrinks. For example, ABS average shrinking is 0.5%. That's why it is harder for printing, it warps, it needs an enclosure. But even PLA will shrink too, very minimally, but I noticed this on some bigger parts. Carbon fibers will reduce this shrinking, we will get better dimensional accuracy, but sometimes they can cause some problems. Sometimes I get a filament and I print the part, and when I measure it, it is actually bigger than in design. I mean, how is this possible if every filament shrinks? Well, the explanation is actually that it will expand and we get some overextrusion. Something similar to those foam filaments, if it is full of moisture, that a micro water drop will boil inside the nozzle and push out more filament. And we will get some overextrusion, some additional offset in that printed line. This may be a good method actually to check if the filament is wet. Extrude exactly 50 mm of the filament, and when it stops with extruding, but of course for this we have to see the gears, cut the filament and follow the oozing. If it is bigger, then it is full of moisture. If it is small, then it is more or less dry. I noticed in most cases this overextrusion is very visible and it will create very rough, ugly surface. Fiber reinforced filaments are sensitive to these nylons, but sometimes it is not so obvious and the surface quality may be acceptable, but we can notice only the problem by measuring the part. So I created this presentation and I will explain it step by step. Dimensional error in X and Y comes from 3 main sources. Scaling effect, material shrinkage during the cooling, affects large and small parts proportionally. This will be a multiplier. Constant offset, overextrusion wet filament fiber-filled materials, and this adds a fixed dimensional error. And then we have printer motion accuracy, belt, ease test, backlash, and assume it's correct here. I will use H2S, which is calibrated using a vision encoder, and I will concentrate only on these 2 properties. Maybe you're familiar with this object, and I know that I would get comments like, just use a cauliflower. Yes, but it's too complex for this demonstration, and I want to keep it simple, like this rectangle, for example. This is the equation where D is the design nominal CAD dimension, M is measured printed dimension, S is the scale factor, accounts for the material shrinkage, and C is constant offset, systematic error, overextrusion, and similar. But how can we get the S and C? Well, for example, we can print 2 objects, and then we have this equation 2 times. So S and C are 2 unknown variables, but with the 2 equations, it can be calculated. This is for the S, and this is for the C. And I created small goals for this video. Goal is to create exactly 100 mm object. And this is the equation, so this will be the measured value. And from this, the design must be calculated from this if I know S and C. And also I want to check if method works with inner dimensions too. For example, I have this rectangle with the 50 mm inner dimension. Equation is very similar, but now that overextrusion is reducing the size, so this is the minus C and not plus like with the previous, and from this I can calculate the design length to get exactly 50 mm. Few notes. Shrinkage S can be compensated directly in the slicer, but constant offset C cannot be compensated automatically, but of course the best results occur if we dry the filament where the C is almost 0. By checking the S with dry filament, for example if it is new or after longer drying, because sometimes even new is not completely dried, we can later detect if the filament absorbs some moisture. But of course the main aim for this video is to understand the physical principles behind the dimensional accuracy. First filament in this test, tin Mori carbon fiber reinforced PETG. And it is 1 year old, stored in a resealable bag but without drying. Two objects created in a slicer, 40 and 250 mm long, completely different settings. This is the printing, nothing special. Actually, this surface looks really good. Looks like dry filament, but let's measure it. This is the first layer, so I'm measuring above the elephant foot. Aligning, I have to be very accurate here. Okay, looks like a bad example of the filament. Now let's measure the bigger one, and last time I got few comments that you cannot see the vernier caliper. Well, here it is, I bought now a digital one. Oh, it is hard to get it in a frame, aligned. 249.55. So these are my values for S and C, and I already calculated it. If I want 100 mm long object, I have to create in design 100.13 in this case, and this is for the inner dimension 50.19. Let's print this. Again, objects created in a slicer, 100.13 mm, and this is the negative part, 50.19. And after the slicing, the negative part will be subtracted from the object. And here they are. Let's measure them. Let's start. This should be exactly 100 millimeters. 100.02 millimeters. Okay. And now the second object. This is the bottom part. Theoretically, this is now 50 millimeters, but I'm not sure if the method works with the inner dimensions too. And it's a little bit hard to find the center, and I want to avoid the elephant foot. 49.99. Wow, okay. One more attempt, and I hope I will have more luck with this one. This is PETG-CF, glass fiber reinforced PET, and that corner bracket I show you is printed from this filament, and I know that it has to be dried before the printing. Let's try it. So I need to start with the printing, and I can see that it is in very bad shape, full of moisture, continuous oozing, and I believe that here that value of the C will be very significant. I don't know, the surface quality looks okay so far, but that oozing was not normal. That's huge. It's full of moisture, I'm sure. It's printed. Let's measure them. Again, avoiding the elephant foot. 40.17 millimeters. And now the big object, but it's a little bit harder for the framing. 249.49 millimeters. I already did the calculation, values for S and C, and only from this C, almost 0.3 millimeters, I can see that it is full of moisture. I calculated the 100 millimeters should be almost accurate, 100.02 in design, and the inner dimension 50.463 millimeters. Let's print this. Let's start with this 100 millimeter version. 99.96, okay, a little bit off, but quite close. And now the inner dimension. This should be 50. $49.98. Just one more time to clear something. This is not the correct method to get accurate parts. I did this just for demonstration, but actually this method may be good to see if the filament is wet and maybe it needs some drying. If that C value is not near zero, then maybe yes, the filament needs some drying. I know today's trend is that those calibration cubes are completely useless things and we shouldn't use them at all. But I'm not sure if you're following me, so smaller parts are more sensitive from this C value and less sensitive from the shrinking. So if you print a calibration cube or just print a D6 dice and measure it, 20 millimeters, there, let's say ABS, shrinking 0.5%, that's approximately 0.1 millimeters. And in this case, if you saw the PETG-CF, we have that C value of 0.3 millimeters. So very easy, just with printing of calibration cube, we can see or predict the estimate value of that C constant. I think I am starting to be too complicated. I should end the video now. I hope I could give you enough information to understand all this process. And if you see the hi button, please click it. And thank you for watching this video until the end, and happy printing.